Hi everyone, welcome to our presentation on how to implement a CNN and LSTM model for automatic image captioning, and, specifically, how such a model can be used to do molecular translation. Before we get into the content of our presentation, however, we would like to briefly introduce you to our team.
Hi everyone, my name is Griffin McCauley and I'm a junior majoring in applied math and economics here at Brown University. In addition to this, I'm also a member of the varsity track and field and cross-country teams.
Hi everyone, my name is Ethan Huang and I'm also a junior here at Brown studying applied math. In addition to that, I'm the founder and president of the Starting 11, an NFL content platform.
The problem domain we based our project around was that of converting molecular structure diagrams in skeletal form to their corresponding INCHI labels. In the field of chemistry, it has been common practice for decades to represent chemical compounds by their structural forms in what is known as the skeletal formula. Past publications are full of these diagrams, but now, as we become increasingly reliant on having computers parse documents and interpret these molecular images correctly, it is of tremendous importance to come up with a way to convert these structures into a form that can be readily understood and manipulated by a machine. The first step towards achieving this occurred in the early 2000s when scientists from around the world came together to develop the International Chemical Identifier, or INCHI label, which we use to represent any compound's specific composition and bond organization as a machine-readable string. The creation of INCHI was a monumental achievement that helped move the field towards a more digital-friendly form, but this new labeling system also left decades of old publications with the skeletal structure diagrams to be forgotten and underutilized. In order to help expand access to previously published chemical research, it is imperative to develop a way to accurately and effectively analyze published scientific documents and identify the presence of known compounds. Having a model that can peruse old papers and determine the presence of known chemical compounds will speed up current innovation by helping researchers avoid the pitfalls of re-exploring or republishing already documented chemistries.
A primary barrier that has prevented such a solution from being found at this point is that most public datasets of these skeletal formulas, along with their corresponding INCHI labels, are too sparse for contemporary machine learning models. And even the best models can currently only produce accuracies of roughly 90% under ideal image conditions. This is not typical for scans of old scientific publications. While this has caused progress in the mission to stagnate, thanks to the team at Bristol Myers Squibb, a dataset containing over 4 million structural images and their corresponding labels has been made available, and this is what we will be using to train our model on and hopefully expose a niche but vital application of machine learning techniques.
Our goal for this model will be to accurately and efficiently convert structural diagrams into their corresponding INCHI labels. And the way we will evaluate the success or failure of such models is by their Levenshtein distance. The Levenshtein distance measures the number of edits that will be necessary to turn one string into another, either by insertions, deletions, or swaps. In order to get a more clear understanding of the dataset we had available and the problem space we were facing, here are some examples of the molecular diagrams and their corresponding labels.
The scope for this project can generally be split into 3 phases. The first phase is research and exploration. Here, we seek to thoroughly investigate the problem at hand and learn from the work of existing models. After perusing various notebooks in Kaggle's wonderful public community, we decided to center our project around a particular pipeline. Due to the complexity of the problem at hand, we believe that carefully studying and replicating this process is a meaningful endeavor in itself, but felt compelled to incorporate some original elements into our project. Therefore, in Phase 3, we added a series of significant improvements that allowed us to take our replicated-based model to the next level.
The first thing we did when approaching this problem was try to get a better understanding of the dataset we were working with. The most notable feature of it by far was its magnitude. With over 2 million training images, this dataset was on a scale we had never encountered before and would cause us to have to really hone our data management and manipulation skills over the first portion of the project. We will save our discussion of how we handled the image data for a few slides, but for now I will just say that the images included in the dataset proved to be of different dimensions and qualities and would need to be standardized later on during pre-processing to make sure they were all a fixed dimension when being fed into our CNN. The labels themselves contain a lot of useful information as well. They allowed us to see that each of the 2.4 million examples we were presented with was unique, and that the varying length nature of them would fit well with the NLP-esque framework we had anticipated. We also found by analyzing the strings that there were 38 unique characters which would become the token elements for our model, not counting the out-of-vocab tokens for the start of sequence, end of sequence, and padding, and that nearly all of them were under 200 characters in length, an important thing to note since we would need to set a maximum output length during training and inference to make sure we didn't accidentally produce an infinite length string with no end sequence token ever being generated. Once we had this high-level understanding of some aspects of our data, it was time to begin the challenging process of actually loading in and working with such a massive dataset.
To continue our discussion of the data loading and cleaning process, we would like to touch on a few components of our process. Since we were used to doing all of our coding in Colab, our first strategy was trying to upload the zip folder containing all 2.4 million training images onto Google Drive and unzipping the folder in Colab. This ended up failing due to insufficient disk space, and even when we tried manually loading the data in small batches, the GPU was unable to handle the training process. Eventually, we realized that since our base model was located in the Kaggle environment anyways, that it might make sense to relocate our data loading process to Kaggle 2. This allowed for a seamless extraction process since all competition data can be easily linked to any Kaggle notebook. We ended up storing our images in the Google Cloud Storage in TF Records format, which made our data compatible with TPUs.
Once we successfully had our data in an accessible format, it was now time to begin building up the components necessary for our model to train and do inference on these image label pairs. The first object we built was the vocabulary of possible character tokens, which we constructed by first putting in the special start, end, and pad tokens, and then added each novel character encountered in each of the labels in the dataset. This process resulted in a vocabulary of 41 tokens total, the 38 unique characters plus the 3 special tokens. Once we had this fixed vocabulary, we were able to turn it into a dictionary, which will allow for quick tokenization of characters and will let us seamlessly map from characters to numbers or numbers to characters. These dictionaries were then saved as pickle files so we could move them around to our different environments.
Next, we felt that it was important to devote some attention to the images themselves. Since the images provided to us were of varying quality and dimension, we decided to crop the images to a fixed dimension by zooming in on the diagram. This also minimized empty background space that wouldn't be particularly useful to the model. We also defined a few functions to further touch up the images by removing extraneous pixels that didn't seem like they were part of the structure and also filling in missing pixels. Finally, we experimented with color. Our final pre-processed molecules, as you will see later, are white text on a black background, since we later convert the RGB pixels to grayscale.
At this point, we were now able to turn our attention to the model architecture. As previously mentioned, since we are attempting to convert from images to unique text strings of varying length, we are going to need to have a model that first applies a CNN to the image input and then linearizes the output of this CNN in a sequential format that can be fed into a decoder which utilizes either LSTM layers or GRU layers. The general design of such an architecture can be seen here, and after browsing the public Kaggle notebooks, we found one that seemed like it would provide a strong backbone for us to base our construction upon. This notebook can be found at the link included on this slide.
After completing the replication process of the public Kaggle notebook that we chose, we had a base model that was ready to be improved upon. This base model achieved its best Levenshtein distance on the validation data at epoch 8 with a score of 16.9, but the model started to diverge after that point, which caused the Levenshtein distance to balloon to about 22 by the end of the 10th epoch. We started to brainstorm ways in which we could make meaningful improvements to this promising yet somewhat unstable base model. The next few slides will examine these changes in detail.
In our model, the encoder cell is simply running the input image through a loaded-in CNN and then flattens the feature maps of each channel to produce a sequence whose length is equal to the number of channels and whose dimension per element in the sequence is equal to the dimension of the flattened feature maps. The initial base model we had constructed used EfficientNet B0 as the CNN in the encoder, and due to the fact that the CNN is so vital in this process, since it is essentially responsible for determining the sequence length and the embedded hidden dimension, this seemed like a logical first component to modify to try to increase our model's complexity and improve its performance. After reading through some articles online and comments on other Kaggle notebooks, we came to the conclusion that our best solution would be to swap in EfficientNet v4 in place of the older version of EfficientNet. Sticking with the pre-trained EfficientNet family of models was a clear choice, since as you can see from the diagram provided, these models offer the best performance for the lowest number of parameters, which is crucial for us since we are already dealing with excessively long run times brought on by the magnitude of the dataset.
After upgrading our image classifier, the next logical component of our model to experiment with was the attention mechanism. Two of the most common methods for computing the scores that govern the attention weights are Bahdanau and Huang. Since our base model used Bahdanau attention, we decided to test out how our model would perform using Huang. The key differences here are that Huang typically uses some form of dot product to calculate the scores, and the context vector is combined with the decoder input before getting embedded to the hidden state, as you can see in the diagram. While both forms of attention produced a steady training process, due to having a larger number of learnable parameters, Bahdanau was able to converge faster. For this reason, we decided to stick with the original attention mechanism of our base model.
Since we decided to stick with the Bahdanau attention, this allowed us to not have the decoder dimensions and attention units be tied to the encoder dimensions. Modulating these hyperparameters up and down individually and in tandem let us see how each one affected the model's performance. What we found was that increasing the decoder dimension provided our model with more complexity due to the larger number of trainable parameters, and this resulted in better Levenshtein distance scores. This finding was consistent with the fact that increasing the number of parameters in the encoder also boosted performance. Lastly, changing the number of attention units did not have an appreciable effect on the model's training or validation metrics, so we did not find it particularly useful or helpful for our model under the Bahdanau attention mechanism.
Now, we are ready to train the model. The custom training loop that we implemented used teacher forcing. This means that instead of using the predicted character as the following input, the actual character is used as the input, which prevents the model from producing a divergent sequence. As usual, we back-propagate the loss with respect to the trainable parameters and store various metrics along the way to organize our results. Finally, we opted to use a step exponential decay learning rate scheduler on the Atom optimizer.
After establishing and setting all of the model architecture and training parameters as previously described, we ran our model for as many epochs as the Kaggle site would allow us in order to find our model's optimal performance capabilities. After 9 hours, we hit the maximum consecutive training time allowable during epoch 32, and although the trajectory of validation metrics indicates that our model was continuing to make marginal improvements, we were already able to see that by epoch 31 under this new configuration, we were seeing Levenshtein distances far below any we had previously achieved. Through our modifications, we had successfully brought the original distance down from 16.9 all the way to 7.4, thus marking a tremendous improvement on where our baseline was. This Levenshtein distance score of 7.4 that we achieved would place us 120th on a Kaggle leaderboard of nearly 500 teams at the moment, which is quite an impressive jump from where we started.
Finally, let's take a look at an example. The graphic below displays a molecular diagram from the validation dataset, the actual Inchy label, and the label that our model predicted. As you can see, our model does a good job of following the general structure of the character string, with a few errors here and there. This specific prediction has a Levenshtein distance of 17, which is quite a bit higher than the average distance. Indeed, we found that our model performs better on diagrams with shorter corresponding labels and plan on investigating how to improve our model's ability to predict longer strings in the future.
In conclusion, this project has allowed us to engage with many aspects of both the data management and modeling sides of deep learning. The most vital skills we have gained from this experience are being able to work more effectively with massive datasets and more deftly navigate the cloud storage systems that allow them to be accessed and housed. We were also able to further improve our handling of TF records and appreciate more thoroughly just how powerful this format is when dealing with datasets of this magnitude. In terms of what we have learned and improved upon on the deep learning side of things, we now have a far stronger understanding of how to construct and implement models that combine elements of both image and sequence data analysis. One specific area we feel we gained an even greater appreciation for and deep understanding of is how the attention mechanisms perform their transformations and how they can be modified to benefit different tasks. Overall, this project has helped us greatly improve the skills necessary for performing deep learning on a large scale, and we are excited to get this opportunity to get a hands-on experience working at the intersection of CNNs and RNNs.
You can find all of the specific components of this project, which include the slides for this presentation, in the link in the description below. We would also like to take the time now to clarify that any metrics reported in the presentation reflect the model's performance on the validation data, not the actual test data. Since the deadline for this competition is still over a month away, we hope to continue making appreciable improvements to our model before officially submitting our notebook, and are confident that our model's success on the validation data will generalize to the testing data set.
Thank you so much for watching our presentation, and we hope you enjoyed.